Hi, everybody. Sorry for being late. There was a problem with our laptop, so we had to use the other laptop. So today we are going to talk about Ghost in the PLC, designing an undetectable programmable logic controller rootkit via pin control attack. My name is Ali Abbasi, and I'm a PhD student at Distributed and Embedded System Security Group at University of Twente in the Netherlands, and visiting researcher at Chair of System Security of Ruhr University Bochum in Germany. I am doing some system-level security for PLCs there. Majid?
Okay. Hello, guys. I'm Majid. I'm Research and Development Engineer at Quarks Lab. I am involved in this research with Ali as an independent security researcher. So today I'm not representing on behalf of my current or former employer.
All right, so today we are going to describe our work. So just one thing I have to mention, that this is not all of the research we did. Basically, what we did today had some components about actual physical process exploitation, which we can't expose because it was part of an EU project. But we are going to expose the details about the attack itself. So it doesn't contain process exploitation because we looked at a specific process in different utilities to exploit them. Anyway, so today we are going to first give you some background on existing attacks and defenses for embedded systems. This is important, maybe not exactly fully what we were doing, but it is important because we wanted to look at existing active defense and attacks against embedded systems, and then we look at them and see which one of them are actually applicable to PLCs. And then later, we are going to the core problem, which is a pin control, and we give you a background on pin control, and we explain the problem with pin control. It's not, well, we believe that it's not a software problem, it's mostly a hardware problem, and then we explain our rootkit variant of our attack. We decided to add some stuff about non-rootkit variant of our work. We will have some demos, including a demo in a real PLC, because again, there was some comments about our work, which we decided to do it in a real PLC as well, and we'll have some discussions. Yeah, so first of all, what this talk is about and what it's not about. So the talk is basically trying to uncover existing design flaws in PLCs, and we believe that this kind of attack can be used in future by the attackers. But today, with the situation we have in the embedded system, and especially in PLCs, we believe that there are far easier attacking techniques. But of course, the vendors, which some of them actually are here and actually did lots of things, they are trying to defeat those kind of trivial attacks. Majid?
Okay, so this research wasn't about developing another version of a Stuxnet. So we're not going to unveil any fully functional rootkit. Like, it's not about a single binary that you can add everywhere on every PLC with any operating system or any architecture. We're not going to talk about any vulnerability discovery technique or any exploitation techniques. So there's also no zero-day to leak. And we consider that our attack is cross-platform because the underlying flaw is not related to any operating system or to any hardware architecture. So it's the flaw is a general flaw in embedded system, which Ali is going to explain later. And of course, we are not going to name any vendor, so no names and shames. Okay, so first things first, let's see what is the critical infrastructure. The critical infrastructures are basically the element of the infrastructure that, if lost, could pose a significant threat to the system, service, and communication. For example, the electrical and nuclear facilities, the water purification, the gas stations, and of course, military and transportation. Okay, based on our previous experiences, the attackers are mostly state-sponsored. They are using 0 days, and they're using highly sophisticated techniques, sophisticated evasion techniques. One of the well-known examples in this is Operation Olympic and Stuxnet, actually. So, like any other attack, before starting the attacker needs to get into the network without being detected. There has been an interesting research in this area, which has been presented at Black Hat Euro 2014 as well, which called defeating the emulation-based network intrusion detection systems. And then once the attacker gets into the network, the second step is to start manipulating the process. There's another good research in this area by Marina Krotofil. It's called Damn Vulnerable Chemical Process. Two good piece of research if you're interested. Okay, so the PLCs are one of the main components of every critical infrastructure. The PLCs are basically embedded systems running an runtime operating system. We can program the PLCs using logics. So the logic is basically a program that PLC executes. And based on this logic, it will make the PLC, for example, to read some value from a physical I/O as an input and do some processing based on that input. And based on the result of that processing, it will update some outputs. For example, imagine that we have a temperature sensor as input, and the logic makes the PLC to read the temperature. And in the processing part, it will see if the temperature is not higher than a predefined temperature into the logic. And if it's higher, it will update some output, for example, turning on an alarm or whatever else. So here we are going to take a look at all the existing attacks and defenses on embedded systems and PLCs. So first of all, we have the attack called firmware modification attack, which the attacker basically take a firmware image and start modifying this firmware and injecting his malicious code, and then uploading this malicious firmware onto the device. The second type is logic modification, which in this attack, the attacker, instead of modifying the firmware, he will try to modify the logic actually, and then upload the malicious logic to control the process. The another class of attack here, which exists for a long time on the PC world, is called control flow attack, which is basically the memory corruption, buffer overflows, and this kind of attacks. The another attack is called authentication bypass, which is a really simple attack, but unfortunately, it's very common. Which is about the default password in the PLCs, which you can see it everywhere, even into the real world system and real critical infrastructures. The last kind here is the ICS malwares, which the malware is attacking directly to the SCADA software, and by controlling the SCADA software, actually he will try to manipulate the process of the PLC. Again, a good example here is still Stuxnet. So for all those attacks, we have the defenses as well. The attestation or memory attestation is one of those defenses. In attestation, the protection, the solution, will try to verify integrity of a system. For example, in memory attestation, the defensive solution will try to ensure that the memory region is not changed, and it will compare it with a checksum. Then we have firmware integrity verification, which is a defense against the firmware modification and logic modification actually. And then the last kind of defense are hook detections, the code hooking and data hooking, which we are going to talk in more detail about them. Okay, so from all those defenses, there are only few of them which match the following requirements are actually applicable to the PLCs. So the proposed solution should not require any hardware modification. And because on the PLCs we have a limited amount of resource, the proposed solution should not pose extra overhead to the device. And then because almost all of the already manufactured PLCs are not supporting virtualization, so if the proposed solution is virtualization based, is not applicable to the PLCs as well. So if we divide all those protection in two basic categories, trivial and non-trivial defenses, we can put logic checksum verification and firmware integrity verification as a trivial defense, and all host-based intrusion detection system in non-trivial category. So the doppelganger and autoscopy JR are two good examples of non-trivial defenses. So let's take a look at how they're working. So doppelganger actually using the memory attestation technique. What it does, it's actually take a firmware image. It will scan this firmware for executable and live codes, and it will randomly install some watch points. And later at runtime, every time that these watch points are hit, it will verify a checksum of a memory region. So as far as the checksum is not changed, it will consider that everything is good, and it will let the execution to flow. Then we have autoscopy JR, the autoscopy JR is basically a protection against the control flow anomalies. It has two different phases. In the first step, it will which called learn, will gather some information related to the execution, and it will function. Is everything good? Yeah. Like function addresses, like return addresses of the function parameter, and this kind of stuff, and it will store all of them in a data structure called trusted location list. And later, in the protection mode, it will compare all the runtime values against this already gathered values, which is called trusted location list. And as far as these two values are matching, it will consider that everything is good and let the execution to continue. So, up until now, we have discussed about two different defensive solutions against code hooking and data hooking. The code hooking is basically when the attacker tries to divert the execution of a function to another part of memory, which he controls, and he puts his malicious code. And once the malicious code is executed, it will jump back to the good function. And data hooking is kind of attack that the attacker not doing anything with the code, but instead it will try. He will try to modify an element of data structure in memory, for example, a syscall table in Linux. Okay. So, like any other defensive solution, the doppelganger and autoscopy JR has their own weaknesses. For example, the doppelganger is not able to verify the dynamic memory. For example, imagine that there is a malicious code is dynamically loaded into memory and then getting executed. The doppelganger is not able to monitor it. It actually doesn't see it. And for autoscopy JR, which using static referencing, and so if the attack is happening in the part of the code and part of the memory, which wasn't monitored actually in the learning mode of autoscopy JR, then later in the protection phase, the autoscopy JR is not able to monitor and do any protection about that attack. Okay, so this was a background about all attacks and defenses. Ali going to give you some background on pin control.
Yay, thank you. Actually, I like these microphones. Like, I don't have to say it loud. So, I guess you're here to listen about the core problem, and this part is actually talking about the core problem. So a background on pin control. Well, let's look at it. So basically, pin controller, like these are the pins in the CPU or SoCs, and basically it's like controlled by a system. We call it pin control. It can be slightly different in different architectures, but they are the foundation. All of them are the same. Majority of embedded systems, 95% of them are actually based on pin-based control. And it consists of two parts, pin configuration and pin multiplexing. So let's start with pin multiplexing. So what is pin multiplexing? Pin multiplexing, very, very simple. It means that you can have multiple functionality in a CPU pin or SoC pin, and you can change the functionality when you want. Usually it happens at a good time, but you can actually change it anytime you want. And usually you have a switch in the SoC, and here is, for example, a multiplex pin, which you can change the functionality to do different stuff. So let's give you an example. You know, I don't want to mention company's name, but for example, you have a phone A and phone B. The company A is very nice and provide you with a SD card reader, so which you can put your phone to you can put a SD card to your phone, increase the storage of your phone. But the company B have the same CPU or SoC, but doesn't have SD card. So what they do is that basically they multiplex the pins, which was being used for SD card operations, and they use it for other purpose. That's pin multiplexing. So you can have multiple functionality, not at the same time, but just you can have multiple functionalities. One of them you can use at a time, but there basically are a switch to you can decide what you want. So next.
Okay.
Thanks. So what is pin configuration? Pin configuration actually simpler. So you know when you have a logic. Now here is example of a very, very basic logic of a PLC. So you say, for example, I write a pin to be input, and this pin number is 24. And then there is a pin I describe as output. You can actually see it here too. This is, for example, output pin, and this is the input pin. And then I decide to turn on and off something connected to this pin. So let's say it's a LED. And I want to turn it on and off every 5 seconds. So what will happen is that basically you describe the input pin here and output pin here. And normally the standard, the rule is that input pin, you can only read from it, but you can't write to it, okay? The output pin, you can both read and write from it. This concept which we are talking, actually, you can have different kind of interfaces in your PLC. So you can actually use SPI. I don't know, some PLCs use some kind of serial interfaces which they are talking with their IOs. They are K-bus, D-bus, I don't know, like SPI, like lots of different. But the foundation, the underlying system, we are talking about underlying system. Here are the same. And next. Sorry. Okay. So there is a problem. The problem is that the pin multiplexing itself and pin configuration, so when you say the pin is input or output, there is nothing tells the operating system that the pin got multiplexed or the pin got reconfigured. And that we think is a problem, and we show it is a problem. Majid, next. Yeah, so before I start, let's look actually how PLC is talking with its I.O. in a very, very, very basic way. So usually you have a PLC runtime. What will happen is that you're uploading your logic. Again, we have this sample logic, and we have some inputs, and then updating some outputs. What will happen is that the PLC reads the logic and knows that, okay, so pin 24 is input, and pin 22 is output, so I have to prepare it to be input and output, and then after, it's going to update the outputs every some seconds, and, well, first of all, you can't just talk to the I.O. in a physical memory if you don't have an MMU in your hardware. If you do have MMU in your hardware. And so what will happen is that the PLC will ask where is this address of virtual memory of the I.O. which I can write. And then based on that, it writes the values here. That's very, very basic form of it. Next.
Okay.
So you have to press. Yeah, that's it. That's enough.
Okay.
So what will happen here is that, again, we are going to actually show it in animation and show you the problem too. So assuming that we have a PLC runtime, and so here we are assuming that you are directly talking with the operating system, but it might be a driver or something else that you are talking. So it might be not the case that you are directly talking to it. So what will happen is that PLC says, okay, I have to use these I.O. memories, right? So these I.O. memories have to be provided for me. You can't talk directly to physical memory because we assume that you have MMU. And then it will ask operating system or whatever to map this physical I.O. memory. Majid, you are too fast. Can you not do that? Yes,
animation
it's fine. Now you just went. Don't do it. But don't do it too fast. So you have a physical I.O. memory. The PLC runtime or driver or whatever, it asks for physical I.O. memory as a virtual memory. And what will happen is that you basically have a mirroring between these two. So then, let's assume that this is our logic. So we want to LED blink every 5 seconds. And the input pin, which is pin 24, is the input pin, and pin 22 is the output pin. So that's actually basically the logic you see here. So pin 24 input, pin 22 output. And the pin 22, for example, here is connected to a LED. So you are turning on and off a LED every 5 seconds. What will happen is that first, you have to configure the pin configuration. So you say, next now, Majid, now it's time.
Okay.
So you are saying, okay, pin 24 is an input pin, so we write value 0 in the state of the pin. So the pin state is 0, which means pin is input, and pin 22 is the output pin, so we write value 1 to it. And then you basically write it to a virtual I.O. memory. And then basically once you write it via MMU, you are actually writing to the physical memory the same value, right? It's fine. Then you are going to read the values because, well, the logic saying while the pin 24, which is the input, is true, so you are reading values from virtual memory, but actually this value is coming from physical memory. And, well, then you are going to change the I.O. every 5 seconds, turn on and off LED. So basically, off means writing value 0, or on means value 1 to the I.O. pin, output pin. So basically, you turn on and off LED. And this, once you write this value, it will get written to the physical memory again. Okay? So far, so good. Everything is fine. But there is a problem. Go forward. Yeah, more.
Up.
More. So, so now let's go back. So let's assume now we are an attacker. And what we do is that, so we had pin 22 as the output. You remember? So the value in the state register was 1. This time, this time what we do is that we are going to say pin 22 is the input. So we change the configuration of the pin from being an output to an input. And we write it to the state register. And of course, this value gets mapped to the physical memory. So you have now 0 for pin 22, which means this pin is input. It is not anymore output. But nobody knows because you don't have any kind of interrupt or feedback to tell the operating system or whatever that this pin is not anymore output pin. So then the PLC runtime doesn't know about it. So it continues to do the logic which we had, 5-second turn on and off LED. Okay. So yes, so this is getting mapped next. Trying to write and writing the value 0 or 1. So it's write value 0 or 1 to turn on and off LED. But here's the problem. The problem happening here. Once the value want to get written to the physical memory, next, you will not have the right. And that's the problem. So this is why we call it a memory illusion. Because what you see in the virtual memory, which available to any software in the operating system, you see a value 0 or 1, but actually this value never changed here. Okay. So in physical world, you don't have it. In virtual world, you have it. So even if you go check the values, what you wrote to the virtual memory, you see everything is fine. But actually in physical memory, you don't. Why? Because you change the state of a pin to the input. CPU doesn't accept write operation to the input pin. But the problem, here's the problem, it doesn't tell you that I don't accept it. It just saying it's fine. So no feedback, no alert. So normally what you assume is that once you fail to write to the physical memory, you expect some kind of failure. I don't know, for example, you're copying a file to your SD or memory card. Once you take it out, suddenly you get an error saying, hey, the SD card or USB disk is not anymore available. This is not the case. That's a problem. So what we thought about was that, well, we know about all existing defenses. So we know about autoscopy JR, which detecting function hooking. We know about doppelganger or software symbiote, which basically verify the integrity of executable part of the PLC runtime. So, and of course, we know there are some logic checksums and stuff. So we don't want to do any of these things. Hooking, I don't know, modifying binaries or changing the logic. So we want to use this weakness, this problem which we explain now. There is no feedback. So where it comes, the pin control attack. And basically, pin control attack consists of 2 parts. So it's not just one thing, it's 2 things. So first part, pin configuration attack, which is basically we exploit the configuration of the pins, how you describe it, like in the PLC. And the next is a pin multiplexing attack. And that's the one which is interesting, which we show later, that how we are manipulating the analog data in the PLC. So, and of course, once we do this kind of attacks, the PLC never knows about it. And now I'm going to explain how they are working. But before, we have 2 variants in implementation of our attack. First one is a rootkit variant, and another one is a malicious C code, which we converted it to the shell code for a PLC, which basically do the same. There is a difference between them. So the difference is that in a rootkit variant, we need, for example, root access, of course, because it's a rootkit, right? So if you go next, so you need root privilege, and you need some knowledge of SOC registers. It took us, for any new PLC, it took us for a week to get enough information about SOC registers. I don't think state-sponsored attackers need that much time. And the next one is the knowledge of mapping. No. I think I do it, thanks.
Yeah, okay.
Another one is the knowledge of mapping between I/O pins and the logic. So this is important, but this is available in the PLC. Once you are uploading the logic to the PLC, basically the logic describes all of these things, the mapping between I/O pins and the logic. So it is available there for anybody to read. The second variant, which basically doesn't need root access, but it just needs equal privilege as PLC runtime. So anything that your PLC runtime is running, we need just equal privilege. And of course, beside all of them, we need to have system level access. So we are assuming we are kind of having a control flow attack inside your PLC to get access to it. So that's a, or let's say you are using a backdoor password or whatever. We are assuming control flow attacks because we like more the second variant. But let's look at the first variant first. I forgot that you are not. So in the first variant, we want to precisely manipulate the I/O operation. Okay? So we are going to use something called processor debug registers. It is not something new. It was out there, I think, since 2006 or 7. First time was a Frac magazine. There was an article about it to designing a rootkit based on, well, mostly for Intel architecture, but well, we used processor debug register in our rootkit in ARM architecture to do our attack. Well, what are they? Well, basically, normally, what you have in function hooking, which Majid described, you are like intercepting a function call, and once you might change the arguments of the function to do something you want, or like divert the execution flow and do something else instead of the original operation. What we do is we are not doing function hooking. What we do, we intercept in our rootkit variant, we intercept access to I/O physical, I/O virtual memory. So you remember we mapped the I/O address? Well, we put those addresses into the debug register. Let's go to the next page. Oops. Yeah. So we believe that we by combining a pin configuration problem, which you don't have any feedback, and the processor debug register, we actually can do the attack. How? Well, we put the I/O again virtual I/O memory address, which you are going to write the values, and later it gets written to the physical memory. We are putting those addresses into the debug register, and then once the PLC wants to do something, we manipulate the configuration of the pin or multiplexing of the pin. So here's the example, how it works. Let's say you are going to turn on and off a LED controlled by a PLC every 5 seconds. I want, as an attacker, to change it to work every 10 seconds, like turn on and off a LED. So what I do, and of course I want to be a stealth, so I don't want for example, let's say it's not a LED. Let's say it's a gate you are opening and closing. So it's like, I want you don't know later that I didn't close and open the gate too. So what I do for write, so I have to both do manipulation of write and read operation. So what I do is here, for example, I put the virtual I/O memory address into the debug register, and let it be there. The PLC starts to execute the logic. It noticed, so next step is that the PLC is going to write to the I/O. We intercept the write operation, but we don't change anything there. What we do change is that we change the state of a pin, which is the output pin, because you are writing to it, to an input pin. So we changed its state, we switched it to an input pin, and then we let the execution continue. What will happen is that the PLC is going to write to the virtual memory, but this pin, which is PLC is going to write, is not anymore output pin, because we changed its state from output to input. Doesn't work. So one of your write operations doesn't work. Next time, we can just change it back to the input pin, to the output pin, and it's working perfectly. It's fine. So it's like we are basically changing the process to something else. For read manipulation, it's a little bit harder, because read manipulation actually happening lot more often compared to the write manipulation. So what we do is, again, we put the I/O register related to reading values to the debug register, and then we let the PLC read the values from the I/O. Once we notice that the PLC is going to read the values, we change the state of an input pin, which you are reading, because you are always reading from input pin. We change the state of an input pin to the output pin, and we write the value we want to write. So we can write whatever. If you are reading a temperature from analog data, we can just change the values there to write something else in a virtual memory. And the read continues, but it reads our value. So we will have some demo, actually 3. Right now, we'll have 4 totally, but 3 of them now. And for that, I have to explain what logic we have. This is a simple logic we had. Again, every 5 seconds, we want a LED blink. Okay? This is an example we have in the first 2 demos we have. So we want the LED to blink every 5 seconds, and that's it. So the LED blinking. And we have a real attack against a real PLC. And for this one, we have a LED which blinking every 2 seconds, and we want to change to, for example, not blinking every time it wants. We want it blinks every time we want. Okay, and that's the example of it. So this was the first test bed we had for the first video, which will show it to you. And this is the second video. We covered the name of the company, and that one is not a company name. It was just a power source.
It's not working.
No, you have to put it to the other video. So sorry.
I need to move it to another screen.
Another screen. So let's go back a little bit. So in this example, so we have a LED is turning on and off LED every 5 seconds. This time we are going to do kind of a DOS attack, so we don't let the PLC control it. But we show you that we are intercepting every time PLC runtime want to turn on and off LED. So every 5 second LED is going to turn on and off. So if the value is true, here the LED, so right now LED is on. And wait. Yeah, so PLC runtime here, the value is true, which means the LED is on. If the value is false, it means LED is off. Okay, so that's the basic thing. So you have just LED turning on and off every 5 seconds. So then we are going to actually run our rootkit. A little bit moving forward, I think that's we don't have to. So we are just have a loader. We are just explaining our loader and stuff. Not important. But here now, so as you can see, still LED is turning on and off 5 seconds. Everything is fine. But now we are going to take control of it. We don't let the LED anymore blinking. But the PLC runtime doesn't know about it. Why? Because we changed the configuration of the pin. So, yeah, 21. Yeah. And so now the operation, the physical process actually are not, the LED, as you can see, is not blinking anymore, right? But we show you, we just intentionally made the logs in the kernel log to show you that actually we are intercepting every time PLC runtime is writing to the I/O. So you can see here, but we are not letting the PLC because we basically intercept every call operation, but we don't let the write operation actually happen for accessing the PLC. We change the functionality of the PLC output pin to an input pin. Yeah, and there's a Persian slang right every time there. But yeah, so yeah, as you can see in the physical process, the PLC runtime here saying the value is false or wait for it. Wait, true. But actually, it is not true. The LED is not on and off every 5 seconds. What we see is that the LED is turning on and off every 5 seconds, but it's not. So this one was just a kind of a DOS attack. So we didn't let the process continue. But what about we want to change the actual process? So let's say right now we were doing every 5 seconds the logic, but this time we want to change the logic to work to change every, instead of every 5 seconds, to blink every 1 second. So here, the PLC runtime here in the output, it's false, then get true. It means LED is on, true, LED is on, so it's blink every 5 seconds. And then we load our, basically, rootkit. So this time, we are actually manipulating the process. We manipulate in the way we want, okay? So now LED is blinking every 2 seconds, but what you see here is true for 5 seconds and false for 5 seconds. So the PLC, oops, can you just go back some seconds? Yes, thanks. So again, you see that play. So see that again, it's blinking, but actually the software is seeing that everything is fine. PLC is running every 5-second LED on and off, but actually in physical world, it is not the case, right? So later, there was some comments, I think, in some conference, and we decided to actually have a demo in a real PLC as well. It just quickly, we did it like last week, and we covered the name of the vendor. Thank you. And yeah, and thank you, my student, my master student, who is now working on his thesis for defense against this kind of attack. He just actually asked him to make this video for us. He did it. So again, this time we are turning on and off LED every 2 seconds here. Our attack here is a little bit slower, so it takes time until it's kicking, but you will see that it's true, LED is on, false, LED is off, right? So that's very simple. And then we'll basically load our attack. Thanks, Andre, for making it, if you watch it later. So now we decide to LED to stop and not working anymore. And so you just saw a very fast blink, but then we take control of it. So LED is now true, but it's not true. Then we decide to turn on the LED because we decided it. So let's say LED is start again. But actually, right now, it doesn't work. So we say LED blink, and LED is blinking now. So, but in the control software there, well, the PLC runtime, assuming the control software and the PLC runtime, assuming everything is fine. You don't touch anything. And we don't touch the logic there. So again, we say LED stop, the LED stop, but you see here that the LED, for example, is true, but it's not, because the LED is not on. So that's the problem. So you see completely different things with what's happening in the software, but what's happening is in the physical world. So we basically, again, that memory illusion reflects itself. So you see something else in the physical world, but the operator sees something else in his software. So we decide. So here we did it several times to just show that we decide when the PLC runtime to have to turn on and off the LED. Can you close it? I think we can move on. We'll have another demo.
Okay. No, it's not right now.
Yeah. We have to close this one. So we have 3 demos. So Majid, you want to add something?
Yeah. So before starting attacking the PLC, we start by analyzing the PLC runtime. As you may know, the PLC binaries are not very well protected. But in one of the case, we started working on a binary which was which had basic protections against static analysis and dynamic analysis. For example, in this case, which was quite surprising, in this case the binary is simply packed. As you can see in IDA Pro, about 99% of the binary is data and just few functions that unpacking the code into memory and doing the final jump. The same binary from the same vendor was protected against some anti-debugging tricks as well, which was the parent process attaching to his child process. So this way, the child process was in debug mode, and it not allow another debugger to attach to do the dynamic analysis. But because we knew what we were looking for, we didn't try to bypass those protections. They're well-known protections and very well documented on the internet. What we did, we used strace. The tricky part using strace on some PLCs is that because we have some limited amount of resources on the PLCs, and the strace is generating huge amount of output, it simply crashed the PLC. So what we did, we used a slightly modified version of strace to gather just that kind of information that we are interested for in our analysis. So as Ali has already explained, we are using debug register in our attack. This technique has been introduced in a FRAC magazine by a good friend of mine, Half Dead. It's a good paper if you're interested on this topic. So, if you remember the 2 protections that we have already discussed about, the doppelganger, which was a data protection attack against data hooking, and autoscopy JR, which was a defensive solution against code hooking. So simply just by using debug registers, because we are not modifying any code into memory, we can simply evade autoscopy JR. And because we are loading our module, our kernel module, or the non-rootkit variant, dynamically into memory, the autoscopy the doppelgangers are actually evaded as well. So as you've seen in the demos, we are not doing any firmware modification and not any logic modification.
Yeah. Okay, so we actually analyzed our rootkit too as a performance-wise because we wanted to further do extra work. So here is an I/O fluctuation after I/O. So this is not anymore a simple process which we are manipulating every 5 seconds things. So we put the fastest possible I/O changes. So normally our PLC could change every 4 milliseconds. That was the maximum speed. But we put it, for example, in the logic that every 3 milliseconds changes. So the blue lines are the normal I/O manipulation, I/O working, and this one is basically the PLC rootkit manipulate I/O. And you can see fluctuation is almost even less than actual PLC runtime I/O. So it's kind of show it you can actually confuse it with the noises in the I/O, and that's a bad thing. But there were some bad things about it. There are some shortcomings. First of all, for write manipulation, what we are doing, so basically you are turning on and off a motor or opening, closing a gate. Well, that's not a problem because we had nearly 5% overhead. But the problem was with read manipulation, because if you are changing a process, for example, you have a boiler and you are closing and opening a gate in the boiler, what you want to do is that you don't want that later operators see about temperature in the boiler going higher. So you have to do read manipulation as well. So for that, we had a problem. The problem was that we had 23% CPU overhead, and that was too much for us. So what we did was that we think, before I say it, our rootkit actually we consider real-time features of the PLC runtime too. So kind of it's a real-time rootkit. But anyway, so what we did, we made a second variant of our attack. So we didn't need to have rootkit because there are some good companies around here that they are verifying the driver in the kernel. There are some companies that are doing that, not all of them. And so what we did is said, hey, the PLC runtime itself is not usually is not in the kernel, but it's actually doing the same thing as we do. So why not we can just use the same way as the PLC runtime do to manipulate the process. So we did it, and actually the performance overhead is actually below 1%. We can actually use already mapped I/O addresses by the PLC runtime, or we can actually remap by ourselves the I/O memory, and actually you can run it as a shellcode. So you can use any kind of legitimate request for I/O, device driver, sysfs, devmem. So the second variant, what we did, well, for read manipulation is very simple. You just what you do is that you just simply constantly write the values you want to the input pin. So it's just you just change the state, just write whatever you want. The PLC runtime always read the values you want, mostly. And for write manipulation, it's a little bit more tricky because we didn't want to constantly write whatever we want. We wanted to be more accurate, like the same way as the rootkit was. So what we did, we had to find something, we call it reference starting time. So what is reference starting time? Well, do you remember the example we had, every 5 seconds turn on and off the LED? So it's you don't know exactly from which relative time you are starting writing to the I/O. So you have to know exactly from, let's say, in our word, we can say at 12:30 and 26 seconds, the first 5 seconds starts, and the next 5 seconds will be at 31, like 12:31, for example. So you have to know this is starting time. So once you know this is starting time, which you can just read from the I/O, and then what you do is that right before the reference starting time arrives, what you do is that you set the input pin to the input, the PLC runtime read it, and then you write the value you want. So you just set the pin to the output and write to it, and that's it. So far what we did, actually all of it was about digital control, so digital I/O manipulation. What about analog data? Well, for analog data, if you just want to, especially if it's input stuff, for example, temperature sensor, well, it is very easy. You can just write to the physical I/O memory using the debug register, or Something else is that a technique which we are calling a PC+1, which we were not letting the PLC runtime write to the I/O. But another way, actually, to do the analog manipulation is pin multiplexing. We didn't talk about it, right? Because most of the thing we did was just about changing the input to output, output to input. But what about the pin multiplexing attack? So we actually did a pin multiplexing attack. We have a motor, which is controlled by a PWM, like I/O interface. And what we do is that we multiplex the pin, which is being used for PWM, and use it for other functionality. We basically stop the motor from working, but the PLC runtime assuming that it's working. Yeah, so this is an example of actually you can write the value. So basically analog data is basically multiple digital values. And demo for, you have to just move the video. Last one. I think you have to stop the video first.
Okay.
Yeah. So here you have a motor which is rotating, like moving forward and backward. This is the value you see. It's moving forward, and then it goes back down and like moving backward. So this is the value PLC is seeing. And then what we do is that we are multiplexing the pin, which is used for PWM, pulse width modulation control, and do the attack. Still motor is rotating, but once we load our attack, it's not going to work anymore because we multiplex the pin. Then, wait for it. Yeah. So now the motor stopped working, but what you see in the software is that everything is fine. Motor is still rotating forward and backward, but it's not happening in physical world because motor is stopped because we multiplex the pin. Problem? Kernel doesn't know that if we multiplex the pin. We physically disconnected the PWM controller, but the PLC doesn't know about you don't have physical connection to it. This is crazy. You can actually see here, it's easier. Can I help you?
No, it's okay. No worries. Here we go.
Okay. So, what about other future possibilities? First of all, one thing you can do is actually, we didn't explore it, but there are some other kind of registers in or like functionalities in the I/O. For example, pull up and pull down resistor. Electrical engineers know it very well in the I/O interfaces. And maybe, we don't know, but maybe you can actually disable the pull up, pull down. Well, actually, you can disable and enable them. But maybe you can remotely manipulate the I/O interfaces via powerful electromagnetic field. So you don't need to have actually any code inside the PLC, but remotely via electromagnetic field change the I/O values. Next. So, as a discussion, what we believe again is that for now attackers basically can do far simpler techniques. They can manipulate the logic, they can modify PLC runtime executable, but fixing this kind of attacks, because they are trivial attacks, fixing them are also trivial for vendors. Of course, some vendors are doing that, and they are even taking further step to fixing these problems. You can actually, it is not hard to have a proper authentication. It's not like to having like a proper logic checksum or having a proper PLC runtime integrity verification. But once you have these things in place, then we believe that the next step for attackers is like what we did. Pin control attack is like one of the examples of it. So you don't have to do the function hooking, which there are some active defenses for it. And so yeah, so this is the next step for attackers. Oops, you moved it. Yeah. Okay. So what we believe is that we need actually more focus on system level security of control devices in future, because in future you will have more sophisticated techniques. For example, one of the entrance way to get into the PLC was getting system level access. So once you fix the problem of authentication, the next problem is having, for example, buffer overflow attacks in the PLC. We need something like control flow integrity in the PLCs as well too. You know, it's not just in an Intel board that you have such things, but you need more advanced defensive techniques there too. Well, pin control attack is again, we believe that it's because it's caused by lack of interrupt for I/O configuration and I/O multiplexing registers, and it can have significant consequences in any. It can work basically in any embedded system, but any embedded system which mostly uses its I/O as an important tool. So it can be a PLC, it can be IED, it can be even a car ECU, which we are studying that one. So yeah, so you can actually use it for every other thing. Majid, do you have a solution for us?
Well, before proposing a solution for our attack, it would be easier to changing the default passwords and putting in place some those trivial defenses. But for now, we can propose against our rootkit variant, which can be monitoring the pin configuration in kernel mode. And as a protection for our non-rootkit variant, simply by doing I/O separation and not allowing the unprivileged process to doing I/O operations directly, we can actually mitigate. We can actually reduce our attack. Okay, so thank you for presenting at our presentation. Sorry for those switches between the slides. It would be easier with a remote controller. Anyway, yeah. Everything that has a beginning has an end. So is there any question?
So we don't have a question time.
Okay, we ran out of the time, so maybe we can talk later. Sorry. Thank you.
Sure. Okay.